So go ahead and pause it here, give example 2 a try on your own before I do it. And in reality, you could sit here and watch me do many of these as you want, but you just have to get your hands dirty. You have to make the mistakes in order to get better. Okay? Most of you probably didn't jump on a bike and take off. You had to fall a few times. Okay? Same thing in this class. Let's go ahead and give that one a shot. Come back and I'll make sure that you indeed got what they already told us the answer should be, cosecant squared x. All right, right off the bat here, I noticed that this is another Pythagorean identity. So if you wanted to, you could go ahead and change that out and put cotangent squared x times secant squared x. And at that point, I would just rewrite them in terms of their alternative, which you can either write cotangent as 1 over tangent, or you can rewrite secant squared x as 1 over cosine. Now, I'm going to go ahead and just rewrite each of these as sines and cosines. So I'm going to go ahead and take cotangent squared x and write cosine squared over sine squared. And I'm going to multiply that times secant squared, which is same as writing 1 over cosine squared. And because I know each of those are being multiplied, I can go ahead and actually cancel the cosine squareds, which multiplying straight across gives me 1 over sine squared x, which I then know is equivalent to cosecant squared x. Doesn't get much easier than that, but to show you an alternative version of this, I will go ahead and do it a second way for you, just to make sure that you know that this is not the only way. Okay, so I'm going to start by taking this cotangent and I'm going to rewrite it as like we eventually did. And then I'm going to distribute that to the tangent squared x plus 1. Now, before I do that, I'm going to rewrite tangent as sine squared x over cosine squared x. And then when I put the plus 1, when I distribute the cotangent that I rewrote, that'll be the cosine squared x over sine squared x. And simplifying now would yield all of the sine squareds here and cosine squareds would cancel to be a 1, plus that merely is, if I wanted to rewrite it, cotangent squared x. And like I mentioned to you before, whenever you see squared functions and ones together, you should be thinking of Pythagorean. And the Pythagorean I told you to memorize was sine squared of our angle plus cosine squared of our angle. And because we are dealing with cotangent, I want to take this cosine and divide everything to keep it equal by sine squared. So I'm going to go ahead and do that here and divide each one of these to keep it equal by sine squared. And by doing that, you can see I get a 1 plus cosine squared over sine squared is cotangent squared, and it's equivalent to, what is 1 over sine squared equal to? That is equal to cosecant squared. So we again have proven or verified that these two sides are indeed equivalent. Hopefully you got that on your own prior to me doing either form, and again, you could have found another way. That's great. The cool thing about these is you already know the answer. You just have to verify or prove by using careful identities and algebra combined to show that. And again, you must show it. So go ahead and pause. Think about the things that we've been talking about so far in this section and how to start this, and then try to finish it. All right, hopefully you gave this one a try. It's a little bit more challenging. And remember, there are certain circumstances that, remember, we can't treat them like they're equal yet. So I can't just multiply over by the secant squared t, which they're using for their angle to that side, because then I'm already saying that they are. I have to verify that they are identical or equal. So which of the two sides did you all decide? What's that? I'm just kidding. I can't hear you. It's all hypothetical, right? this is the hard part about making these videos, I would have probably started on the right side. Now, if you're not sure and you want to also work on the left side, that's fine. And make sure that if you're working these out, if there's a point down here that you get the same thing, and you've now proven that they're equivalent, that's just as well as finding one side and trying to make it look like the other. So I'm not going to do 2 or 3 different versions of every single one of these. So from here on out, I'm just going to show you one way, but feel free to explore and try to find another way. All right? I would have started, even though I don't like fractions, that's typically the uglier side for me. I'm looking, am I going to be able to make this look like that? Probably not. But can I take these two things and multiply them out? Yeah. And hopefully you recognize that these are an A plus B times an A minus B. We call conjugates, because the only thing that's different are the signs in between the A and the B. And so I already know when I multiply this out, I'm going to just get the first thing squared minus the second thing squared. Now, could you have FOIL distribute the whole thing out? Absolutely. If I did the 1 times that, it would give me a negative cosine t. And if I did the positive cosine times 1, I would have had a positive cosine. And that's why we talk about A plus B, A minus B being special and giving it that special name of a conjugate, because you would get your A squared times a negative AB, and then plus another AB, and then minus the B squared. And that's why those always cancel out. And working this that direction, we called it a difference of 2 squares, or conjugates, when we multiply it and get that. All right? So just either way doesn't matter, but make sure that you understand what you're dealing with. And then, again, hopefully you recognize that there are squared parts and ones. So I'm thinking right away, my sine squared plus cosine squared of my angle equals 1. Whether they call it x, t, theta, alpha, beta, whatever, it doesn't matter. Okay? Can I get 1 minus cosine squared? Most definitely. Just subtract over the cosine squared. And that will give me that the 1 minus cosine squared angle is equal to sine squared of that angle. So I can actually replace the 1 minus cosine squared with sine squared of my angle t. And you're looking at that on the right side, and you're like, well, shoot, Alan, I still got to get that to be tangent squared over secant squared. Or if you wanted to, you could rewrite this and try to get it to be that. It's totally up to you. In my opinion, I think it's easier to just start working with the right side now. And since the only thing I have on the right side, after doing this and replacing that with its identical version, would be to write this in terms of sines and cosines, and then simplify, hopefully, to be that. So I'm going to start by rewriting my tangent as sine squared over cosine squared, and then over my secant squared, which is cosine squared. Now that obviously looks way uglier than what we have, so we're going to have to do some multiplying, but remember we can only multiply by a 1. So I'm going to multiply this whole thing by the same thing. And I'm going to undo the dividing that I'm doing here by multiplying by the reciprocal, which would just be cosine squared. That then allows me to cancel out the cosine squares on the bottom and on the top. And notice the only thing that is left that is not multiplying or dividing by 1 is sine squared. And so we have proven by working just the right side to get sine squared, and then just the left side to get the same thing, that these have to be equivalent. Verification. Done. All right, hopefully you're able to do that in one of those two ways, whether you started on this and then you actually could have taken that sine squared and got very creative to try to get these. If you want to divide that by 1 over cosine squared t to get your tangent, then you also would have had to have done it on the bottom. And that actually would have been a lot less time, because if you look at that and multiply straight across, you get sine squared over cosine squared, which is tangent squared, over, multiply 1 times that, you get 1 over cosine squared, which is secant squared. And that's what they wanted us to get on this side. Sorry, I changed from x to t. Should be t. Okay, so again, many different ways to verify, work through these. All you got to do is find one and make sure that you follow the rules of algebra and now these identities properly in trig. So let me give you a little bit more challenging one with this example 4. Go ahead and pause it if you're up for it. You are. Try it. You can do it. And see if you can either get the left side to look like the right, or the right side to look like the left, or work with each individually down until you find something that they can both be equivalent to. All right, go ahead and pause it, give it a try. All right, hopefully you didn't just go around in circles here. You were able to actually come up with one side or the other. If I was to pick a side of which one is quote unquote uglier, the one that's a little bit more difficult to work with, since they're both fractions, what makes fractions fractions are the denominators. That's what I'd be looking at. And since this one has more than just that one, I definitely would be working with this. Okay, so I'm going to start with that. And remember, the only thing I can do to that to change the look of it, but not the value of what they've given me, is multiply by that fancy 1. And since that is a secant x and a tangent x that is being subtracted, I know I'm going to have to multiply by whatever I do on the bottom, the same as the top, but I'm going to make it a conjugate pair by making, instead of the same being the negative that it was here, I'm going to make it a positive. Now again, I'm only doing that on top because hopefully you notice that if I got rid of all of this, you can see that this is just a 1. Anything divided by itself. But I'm going to start on the denominator, because I know that this is my a minus b times a plus b. So I'm going to end up with my denominator being the first thing squared minus the second thing squared. Now for the top, I'm going to have to actually do a distribution, where cosecant, I'm going to go ahead and rewrite as 1 over sine x. And then secant, if you want to rewrite that, you can write it as 1 over cosine, and tangent as sine x over cosine x. So when I distribute the 1 over sine to the 1 over cosine, I would end up with plus, when I do the distribution of the second thing, the 1 over sine x to the sine x over cosine x. The sines would actually cancel out, so that works out a little bit better. But I'm actually not going to do that. I'm going to leave it because I know that I'm going to need a common denominator. And if I leave the sine x times the cosine x on bottom, I'll already have it. So again, just looking ahead, thinking before I do it. Don't listen to Nike. Don't just do it. All right, think about it before you do it. All right, and then the 1 times the sine x on top would stay. Now again, I could have canceled those, but I want, in order to add these fractions, a common denominator, and I already have that. Okay, so next I'm going to go ahead and try to rewrite that a little bit more to simplify by doing what it says on top, because now I have common denominators. So I'll have 1 plus sine x over the sine x cosine x. Here's the problem. That's just the numerator. The denominator, hopefully you recognize, has squared terms. And whenever we have squared terms, remember I told you to think of the Pythagorean. Is this one of my Pythagorean identities? If you need to look it up, that's fine. Otherwise, remember, we can always come up with it by simply trying to get those values. And in this case, secants and tangents, I know I'm going to have to get a tangent by taking the sine squared, dividing by cosine squared. And that would give me tangent squared plus 1 equals secant squared. But they wrote it as secant squared minus tangent squared, so I'd have to simply subtract that over. So now I know that this is actually equivalent to 1, which is beautiful because now I don't have that big old nasty fraction. So now I'm just working with this, and I still need to prove, verify, show that it's equal to that. So we got a little bit more work to do. I got my 1 plus sine x on top. It's saying to divide by sine x times cosine x. So sometimes if you don't know what to do, think about what you're trying to get. What is your end goal? Well, I don't really want to get these yet. I'm focusing on the denominator. And I know I have that. I just need to get rid of this. And how would I get rid of that? Remember, can't change your fraction, but you can change the look of it by multiplying by a fancy 1. And if I only want the sine in the denominator, I'd have to divide by cosine to get rid of it. So I'm going to put multiply by 1 over cosine x to each of these. Because when I throw this all over 1 and this all over 1, then I know in the denominator what's going to happen is cosines will cancel out. And I will only be left with a bunch of 1s multiplying, dividing to my sine, which is what I wanted. On top, I'm going to have to divide this cosine into that. And if you take 1 over cosine x, that's equivalent to just saying secant x. Much easier to write than 1 over cosine. Plus, then I'd have to multiply that 1 over cosine x to the sine x. And when I take a sine and divide by cosine, we said we could write that as tangent. And if you notice, that's exactly what we needed to verify and prove that it's equal to on the other side. Now again, that's just one way to do it. There's many others. If you wanted to work the left side and try to get it down to something even simpler, by all means, as long as you show that the left side and the right side independently are equivalent, then you have verified and accomplished what they asked you to. So again, just increasing the difficulty a little bit here. And of course, more fractions, more going on. Here's our 5th and final example. Give it a try. If you get this one right, I'm very confident that you will do well in this section of homework to practice, master it, and then hopefully be able to move on and do well on the quiz or test. So since this one looks equally hard on both the left and the right side, I'm going to go ahead and try to work both the left and the right one at a time independently to see if I can come up with some alternative third version that I can then say is equivalent and prove that these two fractions or expressions are equivalent. So I'll go ahead and start with the left side. And again, some of the techniques I mentioned to you is if you're not sure where to start, either do what it says, which sometimes means multiply, divide, whatever, or rewrite in terms of sines and cosines. So if I rewrote this, I would have 1 over cosine, that is an alpha for our angle, plus tangent would be sine over cosine. And that's just our numerator. The denominator would look very similar. It would be 1 over cosine alpha minus, though, sine alpha over cosine alpha. Now, the reason I wrote all this out was just to show you that, indeed, all of this looks really ugly. I'm trying to simplify things, right? But I noticed that these are obviously 1 over cosines. But I also recognize that these also have cosine in the denominator. So if I want to make this look a little bit simpler, remember, I cannot change what I have, but I can change the look of it by multiplying by a fancy 1. And one thing I like about both the numerator and the denominator of my big fraction is that their denominators are all the same. So if I wanted to, all I'd have to do is multiply by the cosine of alpha to everything. And that, when I distribute, would cancel out here and cancel out there to just give me 1 plus sine alpha. And same thing, if I multiplied and distributed to both of these parts, the cosines would also cancel out because we're multiplying. And so now all I'm left with is 1 minus sine alpha. And that looks pretty decent. I might actually just pause there and see if I can't get something similar to that, if not that, on the right side. So I'm going to go ahead and pause there and say, well, can I find that that's equivalent to the other side? And now I'm going to work the right side independently, forgetting about everything I did over here, just focusing on this. And hopefully you recognize that that looks algebraic. I'm going to go ahead and flip-flop these two things because we're adding, I can do that. But I'm going to rewrite those as sine squared alpha plus 2 sine alpha plus 1. And if you can't see it, maybe I'll write it in better terms. I'll say, you know what, let u equal sine alpha. And if that is u, then I can rewrite this as u squared. And if that's u, then I can put plus 2u plus 1. Now hopefully that looks familiar. And now hopefully you recognize that this can be factored as u plus 1 times u plus 1. Now remember, nobody cares about u. I'm just kidding. But we didn't have u at the beginning. So we're going to have to rewrite back in what we originally let u equal, and that was the sine alpha. So even though I know that this can be rewritten to look a little bit more algebraic, simpler in that form using the u, which factors to be this, I then have to rewrite it as sine alpha, which was my u, plus 1 squared, because I have it twice. And remember, that was all over cosine squared alpha. Now remember, you may be wondering, how are we going to get this to look like the other side over here? Well, first thing, I notice all I have are sines. I want to get rid of this. And I'm actually going to rewrite this in keeping it in terms of sines. Now that means this side, I'm actually going to write out sine alpha plus 1 times sine alpha plus 1. Now, since they had it flip-flopped, if you wanted to keep it the other way, I just did that for factoring purposes. If you'd rather rewrite it in the terms that they gave us, there is a reason why they gave it to us that way. You just got to flip-flop those back. It would be 1 plus sine alpha times 1 plus sine alpha. And you'll see why in just a second here. Because I know I want to rewrite cosine squared in terms of sine, because that's all I have on this side. So hopefully you recognize anytime there's a squared part, especially when there's ones, you can replace it with that Pythagorean identity. Now notice I did not do that here because I did not have sine squared theta plus 1. So be very careful with that. It was on the outside because this is what we actually have. No sine squared parts. The whole thing was squared. So remember, sine squared plus cosine squared x or alpha or whatever is equal to 1. If you just want cosine squared, you'd have to subtract over and you would get 1 minus sine squared alpha. So we're getting there. We got all sines now, but that doesn't look like what we needed. So I'm going to factor that because these two parts up here are factored. So that would leave me still with those, the 1 plus sine alpha times itself, which again, shorthand, we could have written squared, but you'll see why I didn't in a second. And then I'm going to factor this, which is actually just the difference of two squares. It's my a squared minus b squared. So I'll write that as 1 plus sine alpha times 1 minus sine alpha. And remember, the only time that we can ever simplify is when we are multiplying. And since these big factors are multiplying, I can cancel those because they are themselves, and anything divided by itself is 1. So notice on this side, if you don't want to write the parentheses, you don't have to now. I get my 1 plus sine theta over 1 minus sine alpha, excuse me, which is the same as the other side. So we have verified that these, which we rewrote as that, and that are indeed the same. All right, so these are going to take some time and definitely some practice. And if you need more practice, feel free to do some extra problems. The ones that I gave you should be the minimum that you do. And remember, if you don't get them at the very first try or the very first way, try again. Sometimes skipping it, coming back, or just trying a new approach. Okay? Feel free to work together on these. Having more heads together definitely will help. Alan, signing off.